we are going to introduce Planck's postulate. Planck stated his postulate before Einstein's hypothesis that interpreted the photoelectric effect. Planck's postulate says that the energetic exchanges between matter and electromagnetic waves, that is when matter absorbs or emits electromagnetic waves, this is called an energetic exchange. So these energetic exchanges between matter and electromagnetic waves are done by well-determined energy quantities. That is to say, the energetic exchanges are not arbitrary. They are performed by well-determined values of energy called energy quanta, which are multiples of a fundamental energy quantity called the quantum of energy. A quanta of energy is a multiple of a quantum of energy. The quantum is a fundamental quantity. The quantum of energy is defined by Planck as h nu, which is the energy of a photon in Einstein's hypothesis, where nu is the frequency of the electromagnetic radiation. H is Planck's constant, and E is the quantum of energy. The quantum of energy, which will be denoted by a very big letter E, is a multiple of the quantum of energy, or n times h nu, where n is a natural number. So according to Planck's postulate, we cannot find an energetic exchange equals to half h nu or 3 over 2 h nu, but we can find energetic exchanges of 1 h nu, 2 h nu, 3 h nu, 4, 5, 6, 7, etc. h nu, integer multiples of h nu. The energetic exchanges between matter and energy are always done by well-determined values that are multiples of h nu. This is Planck's postulate. Now we're going to explain the power of a monochromatic light source. So consider a light source that emits uniformly electromagnetic radiations of frequency nu. For example, the source emits n photons in a duration delta t. The energy carried by the emitted photons is equal to n times the energy of one photon, which is h nu. As a result, the power of the source is equal to the energy delivered by the source, which is equal to E divided by delta T. And this is equal to nh nu over delta T. Now, assume that the source emits an electromagnetic wave in a uniform manner. That is to say that during equal time intervals, the number of emitted photons doesn't change. So we can consider this ratio to be equal to the number of emitted photons per second multiplied by h nu. So we get nh nu. Hence, the power of the light source that emits light in a uniform manner, that is, it emits the same number of photons during equal time intervals, is equal to nh nu over delta t, or nh nu, where lowercase n is the number of emitted photons per second. Similarly, we can define the power received by a certain surface. This is, for example, the power received by the surface, and n is the number of photons received by the surface per second. Then the luminous power received by this surface is nh nu, where nu is the frequency of the radiation that is absorbed by the surface. Now we're going to study what factors affect the photoelectric current emitted by the photoelectric cell. For this, we perform the following setup. This setup contains the photoelectric cell, a galvanometer or microammeter, a DC generator of adjustable voltage, and the voltmeter. This is the experimental setup. The phototube contains the photoelectric cell. Here we have the galvanometer and the voltmeter next to each other. And we're going to cover the cell by a filter that only allows monochromatic radiations of wavelengths 435.8 nanometers to pass through it. Now we should turn off the lights and turn on a lamp emitting white light. Notice how we obtain an electric current through the photoelectric cell of value 5.1 microamperes. The voltage between its terminals is 2.53 volts. We're going to cover the photocell by an opaque plate, for like cardboard, for example. We notice that no electric current flows through the cell, and as a result, the photoelectric effect doesn't happen, since the cathode didn't emit its electrons. The cardboard sheet stopped the light from reaching the cathode, as you can see right here. Now that the light arrives at the cathode, an electric current traverses the cell. That is to say, the photoelectric effect is realized in this case. Let's see what will happen to the electric current when we increase the voltage between the terminals of the cell. As you can see, the value of the current will increase. Let's now approach the light source to the cell and observe how will the value of the current vary. When approaching, you notice that the current in the cell increases. So what will happen when we move the lamp away? The current will decrease. Now let's interpret the increase in the current as a function of the voltage. The voltage between the terminals of the cell charges the cathode negatively and the anode positively. When the monochromatic radiation extracts electrons from the cathode, this is an extracted electron, the electron will move towards the anode. That is to say that the electron will be guided by an electric force towards the anode. As the voltage increases, the cathode becomes more negatively charged and the anode becomes more positively charged. Then the anode has a greater tendency to capture the electrons. That is to say, the number of electrons captured by the cathode each second will increase. On the other hand, we know that the current is the amount of charge flowing per unit time. In this case, the charge is carried by the captured electrons. For example, let's designate by n the number of electrons that reach the anode over a certain duration delta t, and the charge of an electron is E, where E is equal to 1.6 times 10 exponent minus 19 coulombs is the elementary charge. The number of electrons reaching the anode per second increases when the voltage increases, and as a result, the current will increase. So as the voltage increases, the current will increase. Now we're going to explain why the current increases in the circuit when the cathode approaches the light source. We're going to consider two positions of the cathode, position 1 and 2. Position 2 is closer than position 1 to the light source. The medium is assumed homogeneous and isotropic. The source delivers its power over concentric spheres. When the cathode is placed at M2, the power is distributed over a sphere of center O and radius OM2. When the light reaches M1, the power of the source will be distributed over the surface of a sphere of center O and radius OM1. Because the medium is assumed to be homogeneous and isotropic, the power will be uniformly distributed over each sphere. We conclude that the power and the surface area are proportional. Then the power distributed uniformly on the sphere of center O and radius OM2, that is to say the surface area of the sphere is S2 is equal to 4 pi R2 squared, 4 pi R squared being the area of a sphere. In the other situation, the power is distributed over the sphere of surface area S1 equals 4 pi R1 squared. Note that a small part of this sphere is occupied by the surface area of the cathode, which is denoted S. Hence, P2 reaches this area. Then, P2, lowercase p2, is the luminous power that reaches the cathode from the total power P of the source. A power P2 reaches the cathode here out of all of the power P delivered by the source. Then in this case, P2 is equal to the power of the source multiplied by S, the area of the cathode, over 4 pi R2 squared. The power that reaches the cathode in this position will be lowercase p1. P1 corresponds to a surface area S, lowercase s. So P1 equals to the power of the source multiplied by the area of the cathode over 4 pi R1 squared. P is the power of the source, so it will remain the same in both expressions. S is the surface area of the cathode that receives the light. P and S both are the same. But R2 is less than R1, then P2 will be greater than P1. The power received by the cathode when in M2 is greater than the power received by the cathode when placed at M1. On the other hand, we know that the received power is equal to the number of photons received by a certain area per second multiplied by h nu. Let's denote by N1 and N2 the number of photons reaching the cathode when in M1 and M2. So N2 h nu is greater than N1 h nu. We can simplify by h nu from both sides, so we get N2 greater than N1. Then the number of photons received by the cathode in M2 would be greater than the number of photons received by the cathode when in M1. Then the number of electrons emitted by the cathode in M2 is greater than the electrons emitted by the cathode in M1. And as a result, the electric current is greater when the cathode is closer to the source than when it is farther away from the source.